So we're going to start talking about chemical reactions and how we can use chemical reactions to describe relative quantities of substances as they react together. So a chemical reaction is essentially a symbolic representation of relative quantities as a chemical reaction proceeds. So based on the law of conservation of matter, we cannot create or destroy atoms in a chemical reaction. So therefore, we need to balance chemical equations or reactions with numbers that we call coefficients. So just to remind ourselves of some terminology based on chemical reactions, all of the substances on the left-hand side of the chemical reactions are considered reactants. And the plus symbol between those substances indicate a separation of atoms within a substance. And then substances on the right-hand side of the chemical reaction are considered products. And again, the same thing with the plus sign separating atoms from different compounds or substances. In the center, the reactants and products are separated by a yield sign. And when we look at a chemical reaction, how we read this chemical reaction is like the following. CH4 reacts with two O2 molecules to produce one molecule of CO2 and two molecules of H2O. And because these are relative quantities again, I could reread this chemical reaction to, instead of referring to it as a single molecule, I could even say for 1 mole of CH4 must react with 2 moles of O2 to produce 1 mole of CO2 and 2 moles of H2O. So in order for us to actually move on and use chemical reactions effectively in a chemistry setting, the first thing that we need to do is learn how to balance these. So let's try this for a few examples. We're going to try a few easy examples first. And so this particular problem, we have PCl5 plus H2O yields POCl3 plus HCl. One of the easiest methods for especially easy balancing a chemical equations problem is to do a trial and error. And so what I do is typically write every element on the left side and every element on the right side, which should be the same kinds of elements, in a column. And what I do is I go through and I count how many I have collectively on each side. So right now I have 1 phosphorus on the left, 1 on the right, 5 chlorines on the left because of the 5 in the subscript of PCl5, and total 3 plus 1 chlorines on the left, or on the right hand side, which is 4. There are 2 total hydrogens on the left and 1 on the right, and a total of 1 oxygens on the left and 1 oxygen on the right. And essentially what I want to do is try to use coefficients that increase the total amounts of that substance relative to every other substance, and trying to total up the total number of those elements so that they match. So if I look at phosphorus first, these numbers are equal to one another, so I'll leave them there. But it turns out that the chlorines are not. I have 5 and 4. Since you have 2 sets of substances on the right-hand side of the reaction that have chlorines, what I want to do is probably adjust those. And I can do that by adjusting the number of chlorines present with regard to HCl. Now I cannot put a 2 here in HCl because then that changes the substance. So instead what I do is I say that there are 2 more total, molecules or moles of molecules of HCl. And that collectively now changes the total amount of chlorines to 5. That has now adjusted another element that is in that substance, so the hydrogens, that now changes to 2. And since they match, we don't have to adjust the hydrogens. Now if we look at this, all of the elements actually have matched in number on each side, and so we would say that this chemical reaction is now balanced as a 1 to 1 to 1 to 2 ratio of each of those substances. And we typically write that ratio that you see here in order that is written for the substances in the original chemical reaction here. Okay, so that is a balanced chemical equation for our first easy problem. So let's try another easy problem. And this is FeO2, or Fe plus O2 yields Fe2O3. So I write my iron and oxygen on both sides and columns. And I have 1 iron, 2 irons, 2 oxygens, 3 oxygens, and now I need to balance those. So I'm going to balance the irons first, and to do that I need to have 2 irons on the left-hand side, so that will change that number to 2. These guys balance now, but my oxygens do not. So it turns out that you have one substance that contains oxygen on the left and one substance that contains oxygen on the right. You could technically just kind of, it's almost like cross multiplying, but you're taking those subscripts and then placing those as coefficients in front of the opposite substance. So if I put a 3 in front of O2 and a 2 in front of Fe2O3, that now gives me a total of 6 oxygens on each side. But when I do that, that has now adjusted the iron on the right-hand side. So that actually gives me a total of 4. So now I need to fix that on the left-hand side, and that would be actually very easy. I go in and put a 4 in front of Fe, so now that gives me 4. So those balance, and the oxygens balance, and that's your easy second example. Let's try some medium problems. So this is a problem that's a little bit more difficult, and the level of difficulty that is introduced here is the fact that you actually have parentheses in the problem. And so we will again start out by putting columns of all of the elements. You have calcium, phosphorus, oxygen, and hydrogen, and also on the right hand side. And what we'll do is just count your total number to start out with. So there are 3 calciums on the left, 1 calcium on the right. There is a total of 2 phosphorus in one substance and another phosphorus in another substance. So that's 3 total phosphorus elements on the left, but only 2 on the right. For the oxygen substances or elements, there's a total of 8 in this substance and 4 over here, so that's a total of 12. On the left and on the right there is 8. And then for our hydrogens, on the left there is a total of 3, and on the right a total of 4. So now that we have our total number of elements, let's start by balancing our first elements written. Now I will say that when using the trial and error method, there are some kind of sort of general rules of thumb. One of those being, try to balance things that are not oxygen and hydrogen first. So we're going to try to balance calcium and phosphorus first, and then we're going to go back and look at the hydrogens and oxygens and try to work those out. So first of all, we know that there are 3 on the left, 1 on the right, so we need to adjust that number by putting a coefficient of 3 in front of our substance on the right hand side. So this now gives us 3 calciums. So let's actually tabulate total what we have so far now. Since we put that number in, everything needs to kind of be adjusted at this point. So there's 2 phosphorus times 3, that's now 6. The oxygen number is now 8 times 20, or 8 times 3, which is 24. And the number of hydrogens will be 4 times 3, which is 12. So now we need to go and figure out a way to, now that we have calcium balanced here, let's try to move on to phosphorus. So since there are a total of 2 substances that have phosphorus, we need to figure out a way to adjust that number to total up to 6. So keep in mind that if you put any coefficients in front of the substance with calcium that has 3 calciums in it, you're going to then adjust calcium also. And then we'll kind of just have to start this whole process over. So if possible, try to work with the other substance that has phosphorus. And right now this guy has 2 phosphorus elements. Well, if we put, say, a 4 in front of H3PO4, now you have 4 plus 2, that totals up to 6. So now you've got these guys balanced. So what we want to do now is let's go through and count how many oxygens and hydrogens are now present, since we've kind of adjusted that on the left-hand side as well. So there, for oxygen, there's 8 in the first substance, and now there's a total of 4 times 4, which is 16. 16 plus 8 is 24. And so that gives us oxygen is balanced. And now let's look at hydrogen. Hydrogen here is 12 because it's 4 times 3. And then it turns out that we had 12 on the right hand side. So yay, that we are now balanced in this substance. It comes at a ratio of 1 to 4 to 3 for this original written chemical equation. So let's try another kind of medium version of this substance, and then we'll move to some hard examples. So this particular chemical reaction also includes something that has parentheses, which can be somewhat difficult to do. So let's try this out. We'll have nitrogen, hydrogen, chromium, and oxygen. Nitrogen, hydrogen, chromium, and oxygen. And let's just count the total up. On the left, there are 2 nitrogens, total of 8 hydrogens, 2 chromium, and 7 oxygen. And on the right-hand side, there's 2 nitrogen, 2 hydrogens, 2 chromium, and a total of 4 oxygens. So again, try to start with oxygens and hydrogens last if at all possible. So let's just look at the nitrogen and chromium. It turns out these guys are balanced, so then we just move directly into hydrogens and oxygens. Well, let's look at hydrogens first, since they happen to be only in one substance on each side. That makes them a little bit more easy to balance. And so let's start out. We have 8 on the left and only 2 on the right. So really the only recourse that we have here is to put a 4 on the right hand side in front of H2O, and that'll give us 8. And so we're good. So now let's look at, though, the number of oxygens and how that adjusts that number. So we have 3 here. Now we have a total of 4 here. Oh, it turns out that's 7. So this actually balanced relatively easily with a ratio of 1 to 1 to 1 to 4. So that's another example. So now let's go to a little bit more difficult problems that require some actual trial and error and changing of numbers and coefficients and such. So here's an example problem of C4H10 plus O2 yields CO2 plus H2O. It doesn't seem like that this is relatively difficult just by first glance, but once we get started, you'll kind of see what I'm talking about here. So we'll write our elements down. And so I'll kind of take you through my thought process. Again, it would just count the total carbons on the left is 4, 1 on the right, a total of 10 hydrogen on the left, and 2 on the right, and a total of 2 oxygens and on the left and 3 on the right. So let's start with carbon first. Remember, try to do hydrogen and oxygen last. So carbon, let's see, we have 4 on the left. Really easy thing to do is just put 4 on the right. And so we'll put a coefficient here. That'll change this number to 4. But let's make some adjustments because the thing that we changed was the value for oxygen on the right hand side. So now what we have, a value of oxygens is 8 here plus 1, that's 9. And I want you to note one thing. This is through practice of doing these chemical reactions of balancing. When you start to get to elements where you have, say like this one right here, where you have oxygen in one substance and oxygen in another, and then on the other side you happen to have only one substance that has that type of element, the determining factor of whether or not you're going to have an odd and even number is going to be based on what that one substance with the one element on one side has. So note that this O2 is even. Guys, that means that no matter what you do to 2 and what coefficient you put, you're always going to have an even number. So I have an odd value here. That's never going to work. So I'm going to have to make that even. And more often than not, if you have something here that has a single element in it, that's an odd, we're going to have to adjust that coefficient's value to make it an even number of oxygens. That means really only things I can put as coefficients in front of H2O are even coefficients. So 2, 4, 6, 8, so forth and so on. So what I can do is let's try to adjust it based on something else that I know that is also true, and that's the number of hydrogens. So if you look, because if I adjust the H2O, it's going to change the hydrogens. I have 10 here on the left and 2 on the right. Well, something very easy I could do there is put a 5 to do that. But see, remember, I can only put even numbers as coefficients. Well, if I can't do 5, then I have to just double it. I'll do 10. So let's do that. So we'll put 10 here, and when I do that, that's going to now adjust not only the hydrogens but the oxygens total on the right hand side. So let's just count that hydrogens first really quick. Turns out there's now 20, and then the oxygens, how many I have, will be 4 times 2, which is 8 from CO2, and now 10 from H2O, and you add those together, you'll have 18. So now let's go and look at the left-hand side and see if we can kind of fix that total value. Okay, so one thing that we noticed is that the total number of carbons on the right-hand side, or the coefficient in front of C4H10 now needs to be adjusted because you had 20 hydrogens on the right hand side. So let's go ahead and put a 2 here, and that will now give us a total of 20 on the left hand side. But see, now that changes carbon on the left hand side to an 8. And so we might need to do that on the right hand side over here. So what we'll do is we'll go ahead and get rid of the 4. That gives us 8, and that number now is going to be a different value. We'll have a total of 8 oxygens on the right and 8 oxygens on the left. And our hydrogens are balanced with 20 on the left and 20 on the right for hydrogens. But now our oxygens are so kind of like, we've got way different numbers than what we've had before. So let's retabulate the right hand side so that we can figure out what to do with the left. With this particular one, we now know that the number of oxygens here is 10, under H2O, and the number of oxygens now under CO2 is going to be 2 times 18, which is 16. So total those up, that's 26. So really neat thing happens here. There's only one substance that has oxygen on the left-hand side, and it turns out that it's just by itself O2, and we can really, hopefully, based on the value that you get over here, use one coefficient to balance everything back up. And so essentially what I need to do is figure out what number is it that I need to multiply times 2 to get 26. And that's just half of 26, which is 13. So we can put 13 here as the coefficient. That makes this number 26. And that works out all the way around for the left and right sides for each element. And so what you'll notice is that the problems that start to get a little bit more difficult are more difficult because you're having to go back and readjust and change your coefficients and recount. And the numbers of your coefficients start to get fairly high. And so it's a matter of trial and error. If something gets kind of wacky, just erase everything and start over. Or you might want to check how you wrote down your chemical equation just to make sure that you have everything really worked out. Now, for the last problem that I wanted to let you guys try is this problem is actually a really difficult balancing equation problem. And in fact, it's said that if you can balance this particular type of equation, you know how to balance chemical equations and you don't even have to try it again. So, or do any more practice problems. So what I would like for you guys to do is just pause the video for a while, see if you can work on it yourselves, and then when you're done trying, you kind of get frustrated or you finish, once you go back, and then you can watch me do the problem. And I'm not going to talk about what I do, I'm just going to kind of work through it myself, and you guys can check your work. Okay, well, I'll see you in class next time.